Can you define what a rational expression is?
Quotient.
It's a what?
Quotient.
Good, I like that. It's a quotient. A quotient of what?
Polynomial.
Oh, Courtney, have you been studying?
I have my notes.
Oh, good. Yeah, no, I love every answer that you've provided so far. Yeah, it's a quotient, meaning, it's a fraction. And in the numerator, you're going to have a polynomial. In the denominator, you're going to have a polynomial. The most simple example that we looked at yesterday was something like that right there, like -5/4. I mean, that is a rational expression, okay? Then we kind of looked at another one, 4y to the third over 7. Once again, it's a quotient, okay? But now we're really starting to dig into the polynomial territory because you have those variables raised to exponents. And then we looked at more complicated versions. But the idea behind it is you got a polynomial in the numerator, polynomial in the denominator, okay? So then we said, okay, well, if we are dealing with rational functions or rational expressions, we do have to be concerned with the domain, okay? And remember, when you see the word domain, let me get out my marker here. When you see this word domain, you should be thinking x values. What x values can I use inside of this function that's not going to break it? Okay? And this was basically a review for us because we looked at domains earlier in the semester. So, real quick, here's a nice little example. Let me see if I can get a better one here. Yeah, that's fine. So here's our example. Find a domain for h of x equals 8x minus 3 divided by x squared minus 5x plus 6. And just recall the steps. Identify the type of function, find the contradictions, and then write out the domain how the answer wants it. If they wanted an interval notation, draw a little number line, put circles where the contradictions are, and then label each interval. If they want set builder notation, remember, the squiggly, the x, the bar, the x is a real number. Leave a big space. Sorry, I forgot the word and. Leave a big space, and whatever you got for contradictions will go right there. So every single set builder notation is the same. It's just the contradictions are going to be different. So that's all you have to write. Okay? Are there any questions? Good. Then we looked at multiplying and dividing. All right, there we go. Here's our steps for that, which are very similar to multiplying and dividing fractions from all the way back in chapter 4. Okay, you're going to rewrite the problem if necessary. And I gave you just some guidelines. We like things in descending order. And if we're dividing, and this is gonna be really dumb. I hate writing this. But if you're dividing, remember KFC. Keep the first fraction, flip the second fraction, change division into multiplication. Okay? So there's like your little thing to remember on how to do that. So once you rewrite the problem, then you're going to completely factor everything. Okay? Just factor everything. Step 3, you're going to simplify by dividing out factors. And we looked at a couple examples doing this. All right? Now, there is something that I personally like to do. All right? And that's going to be in this example right here. So if we look at negative 3x plus 6 divided by 6x squared plus 6x times 3x squared minus 2x minus 5 all over x squared minus 4. Notice I factored everything. Step 1, it's already written nicely. In fact, we had to actually do step 1, so don't worry about that. But step 1, everything looks good. Step 2, I completely factored everything. And then within step 3, what I did is I rewrote all the terms in the numerator and all the terms in the denominator so that they stack on top of each other. And the reason why I did that is so I can look at this and say, okay, I have negative 3 over 6. That reduces to 1 over 2. Let me get a better marker here. All right. Then I see the x plus 1 in the numerator, x plus 1 in the denominator. So I can reduce them. X minus 2 in the numerator, x minus 2 in the denominator, I can reduce them. And then what's ever left over, in other words, once you're done dividing everything out, what's ever left over is going to be your answer. We have negative 1 times 3x plus 5, and then 2 times x plus 2. Or 2x, I'm sorry, I forgot the little x right there. And that's exactly what we have right here. Okay? And that's really the big review for everything. So, are there any questions? Because what we're going to do is we're going to do a couple more examples, and then we're going to move into the next section. Okay? So, are there any questions? All right, let's go ahead. Let's do this then. So, here's the first one. Why are the cats running around like crazy?
I don't know.
Oh, geez. Okay. All right. So let's see. We'll start off a little simple.
Have fun with math. It is laying.
It's not laying.
Our yard is covered. Right
The yard is covered, not the street.
now. Okay, excuse me, Mr. Science.
Not Mr. Science. It's just fact. All
Okay.
right. Have a good day.
All right, I love you.
Love you too.
Goodbye, Arthur. I love you.
Okay. Are we ready, or do you need some more time? All right. I'll give you some more time. Okay. We good? Because we should be by now. Now this one, don't force it. This is just a completely. Do you know what you're doing? That's what this question really is designed for. So step 1. Let's rewrite. So I keep the first fraction. And I'm going to multiply by the reciprocal of the second fraction. Okay? Step 2, completely factor everything. Everything is factored. Step 3, divide out terms. Now, can we divide out terms in this problem? No. So, all you're going to do is just rewrite it. Call it a day. That's it. Just because you're dividing rational expressions or multiplying rational expressions doesn't necessarily mean that everything is always going to be able to be factored and simplified. Okay? You're going to make sure you're just going through the steps. Now, I will give you this. This problem, 100% you're going to be able to reduce some stuff. Okay? All right, so go ahead and do that one for me. You will be able to reduce some stuff here. Everybody okay? Does anybody need like a push in the right direction? All right. Did anybody get an answer yet? I think that's a good question. All right. Who got an answer? Anybody? Come on, I'm over here dancing.
I have no clue if it's right.
Oh, that's okay. We're gonna test it.
Okay, I got negative 7x. What do you call it? The quantity?
Quantity of.
Yeah. Over.
Quantity of what?
Oh, x minus 2.
Yeah, that's pretty important.
And then over x times the quantity of x plus 4.
All right, so I can tell you right now that's not completely simplified.
Minus the x's.
Minus the x's, okay. So the x's will reduce. All right. It looks okay. Let's see what we get. All right. So first thing I'm going to do, I scan the entire problem to see if I need to rewrite anything. So the very first fraction, the very first numerator, that is not in descending order. So I'm going to rewrite that. Now the denominator, we're okay. And the second fraction, both numerator and denominator, they're both okay. So I'm just going to rewrite everything. All right, good. So there was step 1. Guess I'll just label it. Step 2, let's go ahead and let's factor everything. So the numerator, first fraction, I could definitely factor out a negative 7x. That's going to give me x minus 5. Okay? Denominator, difference of squares. X plus 5, x minus 5. All right, put a multiplication symbol. Second fraction. Numerator, trinomial, no GCF, 1 out front. So I can go directly into this. Put an x and an x, a plus and a minus. Two numbers that multiply to get 10, combined to give you 3. One of them is positive, one of them is a minus. That's going to be 5 and 2. And then the denominator for the second fraction, there is a GCF. Factor out the x to give me x plus 4. Step 3. Let's go ahead and divide things out. What I'm going to do is I'm going to rearrange the entire numerator and the entire denominator so things are stacked on top of each other that look the same. So negative 7x times x minus 5 times x plus 5 times x minus 2. Now my denominator is going to change a little bit. I'm going to put the letter x, which is this one right here, where I just drew that little arrow. I'm going to put that directly underneath the x. I'm going to put the x minus 5 underneath the x minus 5. I'll put the x plus 5 underneath the x plus 5. And then there's nothing I could do with the x plus 4, so I just leave it in the bottom. all the way at the end. From here, I start simplifying. I look for terms that are the same in the numerator and denominator and divide them out. So, give me 1 second because I'm just going to copy and paste this because I'm going to scratch some things out. Oh, that wasn't fun. There we go. All right, here comes the fun part. See you later. The x minus 5s, see you later. The x plus 5s, see you later. Nothing else reduces. So I write what's ever left over to numerator and denominator. And there we go. So, Courtney, I think that's what you gave us, right? Yeah, perfect. You get a smiley face. Isn't that nice? Good job. Are there any questions with how we approach that problem? If you could do this one, you could do them all. Because the process is the exact same. All you're doing, rewriting, factoring, dividing out terms. Going once, going twice, sold. Now, we get into the fun stuff. All right? Let me turn on my keyboard here. That would really help. Section 14.3. Adding and subtracting rational expressions with like denominators. All right. Now, this one's going to be, for us, a little easy. Okay? And the reason why I'm saying that is, like, I hate repeating myself so many times because I sound like a broken record. You already have the techniques that you need to do this. So here's our first objective. All right, we're just going to add or subtract. With like denominators. So here's our first example. It's as simple as it gets. 5 over 12 plus 7 over 12. Now, when you were adding fractions from a long time ago, remember, you got to have a common denominator. If you don't, you need to make it common. But for us, with this first objective, in fact, this entire first section, everything's going to be the same regarding denominators. The key is, how do you write it? Okay? So we're going to be really careful with how we write things. Now, if you had me in a previous class, how I taught you was, once you've established that the denominators are the same, write the denominator once, and then write the entire numerator. Then add. Okay, and there's a reason for that. The reason is you could see things. Okay? Now, where this may get a little complicated is with an example like this. All right? So here's our example right here where we are adding rational expressions, or in this case, we're subtracting rational expressions, okay? Now, in your book, I don't know how many read it. I know I do. In your book, they give you the steps on how to do this. And here's what they say. Now, before you write this down, let me write it first, okay? I'll tell you when to write it down. So in the book, it just says, if P over R and Q over R are rational expressions, okay? Then, and here's what they're saying. P over R plus Q over R equals P plus Q over R, which they're correct, and P over R minus Q over R equals P minus Q over R, okay? Here's what they don't tell you, and here's what I need you to add in. Always put the Q in parentheses, okay? Always put it in parentheses. And here's why. If we look at this example above us, you can see that the denominators are the same. They're x minus 2, okay? The fact of the matter, though, is this. I am subtracting the entire 4x plus 1 away from the first numerator. Does that make sense, everyone? In other words, that 4x plus 1, I'm subtracting that entire thing away. So what you have to do is put it in parentheses, because you have to distribute that negative sign. The number one mistake you will make is you didn't put the second fraction's numerator in parentheses and you forgot to distribute the negative sign. That will be the mistake you make every single time. Okay? So make sure you are doing this. So now you can write this down. Put the Q, regardless, in parentheses. More general, put the second numerator in parentheses when you go to rewrite, which is this step right here. All right? That's the key to this. Your book does not show that. They just kind of assume that you know that. Personally, me, I like to just not leave anything on the table. I want to tell you everything that you need to know. All right, so I'll give you a minute here to write this down because it's a little lengthy. Oh, I didn't even finish the problem. So while you're writing it down, I'll finish the problem and then I'll go over it. Okay, are we good? All right. So real quick, I'll just go over this problem just one more time. All right. The original problem was 1 over x minus 2 minus 4x plus 1 over x minus 2. We're subtracting fractions here. We're subtracting rational expressions. So I rewrite it so that I have one denominator, x minus 2, and I rewrite the entire numerator. And I always put that second numerator in parentheses. So I get 1 minus the quantity of 4x plus 1. Then I have to distribute the negative sign. So that's how I got 1 minus 4x minus 1 all over x minus 2. Okay? Now I just group like terms. 1 minus 1 is 0. So I'm left over with negative 4x over x minus 2. Are there any questions? Because I got a question for you people out there in internet land. Here's my question. Why did I not simplify those x's? Because that's a very common mistake students will make. Why didn't I do it? Give me a reason why. And remember, I'm telling you, if you did that, you were wrong. You cannot do that. So why didn't I reduce those? I think it's a valid question. Somebody help us out? I mean, just take a guess. It's okay.
I have a guess.
Go for it.
I feel like it's because, like, on the denominator, like, it's attached kind of to, like, the subtraction side, so you can't really just, like, take part of it out. Like, if that makes sense, like, you can't just take the x out.
April, that's exactly how I would have answered you if you would have asked me that question. I would have said, you know what? Think of that minus sign as like glue holding the x and the 2 together. Okay? In order for you to reduce that x, you would have to have x minus 2 in the numerator, and you don't have that. Okay? A lot of the times, people will actually just put this in parentheses. And remember, those parentheses act like a bear hug. They hold everything together. Okay? I like the way you said that. So, let's do some examples, all right? Next one. This one's going to be kind of simple. Once again, we're just going to walk through the motions here. Like I said, this one's kind of easy. All right, so step 1, you got to have common denominators. 3x minus 2, 3x minus 2, so we're good. So we're going to write the denominator once and write the entire numerator. Now, the second numerator here, I didn't put it in parentheses, and the only reason why, it's only one number. It's just one term. I don't have to worry about that. Now, there's something that actually happens here that we kind of did in the first problem, but not really. What happens here? Everything reduces. Very good. Everything reduces. 3x minus 2 over 3x minus 2 equals 1 over 1 or just 1. So we learned something extremely valuable here, which is once you add or subtract, once you combine like terms or simplify however you can, you always want to make sure that your answer is always in its simplest form. So what I'm going to do here is underneath here, I'm just going to say, make sure your answer is in simplest form. Okay? You did that a long time ago. You actually did that a long time ago. All right? Let me show you an example of where you did that a long time ago. Just give me 1 second. I got to think about this. So you did this a long time ago. What you would have done is you would say, okay, denominators are the same. So I'm going to write it once. I'm going to take 12 minus 7 in the numerator. Now I'm actually going to subtract the numerator. 12 minus 7 is 5 over 35. And if you were like me, you would rewrite 35 as 5 times 7. Notice what I did there is I factored it. That's what I did with 35. I factored the number 35. And the reason why I did it is so I can see that I have a 5 in a numerator and a 5 in a denominator. And I hate when that happens. And that reduces down into 1/7. So you've already done this, where you had to add or subtract with like denominators, and then you had to make sure your answer is in simplest form. You got to do that with every single one of these. So let's look at an example that we would encounter in chapter 14. So here's our example right here. 4x squared plus 15x all over x plus 3 minus 8x plus 15 all over x plus 3. Now I'm going to help us with this. I'm going to walk us through it. So first thing, I'm adding or subtracting. So I need a common denominator. We already have it. So I'm going to write the x plus 3 in the in the denominator, and write out the entire numerator with my parentheses, okay? So I'm going to get 4x squared plus 15x minus parenthesis 8x plus 15 inside of the parentheses, okay? Are there any questions so far? All right, now let's distribute. So I get 4x squared plus 15x minus 8x minus 15 all over x plus 3. Now I'm going to group like terms. 4x squared, let's see, 15 minus 7 is 15 minus 8 is positive 7x. Minus 15 all over x plus 3. So now I'm feeling good. It's like I subtract, distributed, group by like terms. But now I got to make sure. Is this completely reduced? That's the question of the day. And the only way you're going to know is if you try it. And how do you think I would completely reduce this fraction at the very end? Just give me one word. It's only one word. Starts with letter F. Say it loud, Courtney, and hopefully you said the right word and not the bad word.
Factor.
You're going to have to factor. So even if the numerator factors, you may not be able to cancel out any terms, and that's fine. But you're never going to know that unless you factor. So let's go ahead and let's factor this. AC method, there is no GCF. So get an idea. Plus and a minus, that's my idea. Now, I'm going to take 4 times 15. Oh, man. That equals 60. And the only reason why I said, oh, man, is because 60 has a lot of factors. So we have 1 times 60, 2 times 30, 3 times 20, 4 times 15, obviously. 5 times 12, 6 times 10. 7 doesn't work, 8 doesn't work, 9 doesn't work, 10 times 6, so we just repeated ourselves. So here's what I know. I know of these factors, one's positive, one is negative. They need to combine to give me positive 7. I think that occurs right here. With a negative 5 plus 12. So I'm going to rewrite this with the middle term separated. 4x squared minus 5x plus 12x minus 15. Okay? Now I factor by grouping. So let's group the 4x squared minus 5x plus group the 12x minus 15. In the first group, I can factor out an x. That's going to give me 4x minus 5 in parentheses. In the second group, I can factor out a 3. That's going to give me 4x minus 5. In the second group, I'm feeling really confident because the binomials inside the parentheses match. So I can factor that out as well to give me 4x minus 5 times the quantity of x plus 3. So I'm going to write that back upstairs where my problem is. And from here, we could see that the x plus 3 and the x plus 3 in the denominator reduce. Okay? And I'm going to show that by lightly putting red lines through it. There you go. Hopefully you could see that still. So the x plus 3 in the numerator, x plus 3 in the denominator reduce, leaving us with a final result of 4x minus 5. Are there any questions? All right. So let's think about what's happening here. In the previous section, we were multiplying and dividing, okay? In multiplying or dividing, what you want to do is you want to rewrite and then factor, okay? When you add or subtract, combine the fractions first, factor at the very end. Does that make sense, everybody? So there is a little bit of a difference there. With multiplying and dividing, you're factoring first and then simplifying. Here, you need to combine the fractions first and then you factor second. Does that make sense? All right, so you got to be careful with this. Any questions? All right. Let's go back to chapter 4. How do we find an LCD? For example, let's make this pretty. 3 over we'll leave it 22. That'll be fine. How would I find an LCD of 1/8 and 3 over 22? Ooh. Oh, crickets. Oh, did I stump some people? How would I find this? First, maybe I'm rushing. What does LCD stand for?
Like common denominator?
Yeah, least or like common denominators. Traditionally, we say the least common denominator. So LCD, least common denominator. And what that really means is what is the smallest number that both of my denominators can divide into evenly. So what is that number that I can say this number divided by 8 equals a whole number, and this number divided by 22 also equals a whole number? Doesn't have to be the same whole number, just has to be a whole number. No decimals, no fractions. Nice and easy. So how do we do this? Man, I hit the nail on the head with this one. Eunice, any ideas? I haven't heard your voice in a long time. And it's okay. If you don't have an idea, say, I don't know, float. Okay, that's fine. Just say, I don't know, float. You got to say it just like that. My man, I'm going to show you how, Eunice. I got your back. So here we go. Step 1. Well, let me write this. To find the LCD. Step 1. You're going to factor each denominator. Okay? In the case of numbers, you're going to use prime factorization. In other words, break the number down so you're multiplying nothing but prime numbers. Now, I don't know if you knew that, but you can do that with any number that exists. You can write it as the product of prime numbers. Prime factorization is like a fingerprint for every single number because every number has a different prime factorization. Step 2. Now this is the biggie. The LCD is going to equal the product of unique let's say unique factors from step 1, each raised to a power equal to the greatest, it's lengthy, but don't worry, it's easy. The greatest number of times that the factor appears in any one factored denominator. Like I said, it's lengthy, but once you see it, it's like, oh, okay, I get it. It's just, you got to be very specific. Knowing this will lead us into the next section. So we got to know how to do this. So here's what I'm going to do. I'm going to show you how to do this with 1/8 and 3/22. Okay? So step 1, I'm going to write it in red so you know I'm actually like doing it. So step 1, let's factor each denominator. 8 is going to equal, I'm moving too fast. To find the prime factorization of 8, you're going to do a factor tree. So just give me, I don't care what they are, any two numbers that multiply to get 8. 2 and 4. 2 is a prime number, so I circle it. 4 is considered to be a composite number, which means I can break it down even further. So 8 is going to equal 2 times 2 times 2. All right? Now, I'm going to do 22. Two numbers that multiply to get 22 are 2 and 11, and they're both prime. So 22 equals 2 times 11. So there's step 1. Step 1 is done. Now, what step 2 is telling you to do, there we go, so we can still see step 2. So step 2 is telling me this. It's saying the LCD is going to equal the product, which means multiplication, of unique factors from step 1. Unique meaning different. So if you look at the factors that I have the number 2 and I have the number 11. Those are the unique factors. The question becomes, how many 2s do I have and how many 11s? And that's the second part, which is right here. And this is the most important. So, the LCD is going to equal the product of unique factors from step 1, and these unique factors will be raised to a power equal to the greatest number of times that factor appears and any one of the factorizations. So for example, that number 2, the number 2 appears in the factorization of 8, and it also appears in the factorization of 22. Which factorization do you see the most number of 2's? 8 or 22? Somebody has to unmute themselves and tell me. Say it again. I love it, Abigail. Abigail said 8, and I agree. Now, how many 2's do you see in the factorization of 8? 3 of them. So it's 2 to the 3rd power. Okay? Now, the number 11. The number 11 only appears in the prime factorization of 22. And there's only one of them. So you just put 11 to the 1st. So my LCD is going to equal 2 to the 3rd power, which is 8, times 11, which is 88. And that is how you find prime factor, or that is how you find a least common denominator every single time. Does that make sense, everyone? All right, let's do one more like this. So let's find the LCD for 7 over 20x and 11 over 48x to the 3rd. Okay? Now, I'll walk us through this again because I want you to see everything, okay? Step 1. Let's go ahead and let's prime factorize the denominators. The letter x, we don't have to worry about it. It's just there. All I'm concerned with are the numbers. 2 numbers that multiply to get 20. How about 4 and 5? 5 is prime, circle it. 4, break that down even further. 2 times 2. Now, real quick, eyes on the screen. Eyes on the screen real fast. 20 is going to equal 2 times 2 times 5. Now, this is why I want you to look at the screen real quick. Even if you picked 2 times 10, because those are 2 numbers that multiply to get 10. Watch what happens. You still get the same exact prime factorization. That's what I meant by every single number has their own unique prime factorization. It's their fingerprint. Okay? So it doesn't matter what numbers you pick, you're always going to arrive at the same exact result. Okay? Now, let's do 48. 2 numbers that multiply to get 48. 6 and 8 are the first 2 that come to my mind. 2 and 24 works as well. Okay? Now, let's break down the 6 into 2 times 3. Break down the 8 into 2 times 4. And then the 4 can be broken down into 2 times 2. This is called a factor tree. So 48 is going to equal, and I'm going to arrange this in order. 2 times 2 times 2. Wow, we got 4 2's. 1, 2, 3, 4. Okay. Times 3. So there's step 1. Step 1 is done. Step 2. It's the product of unique prime factors, or better yet, just the product of unique factors. So I see a 2. So my LCD is going to equal a 2 times a 3 times a 5. The question becomes how many 2's, how many 3's, and how many 5's. So if I look at 20, I have 2 2's, but in 48, I have 4 of them. So this is going to be 2 to the 4th, because that is the most I see in one factor. Does that make sense, everybody? Now let's look at the number 3. There's only one. So it's 3 to the first. And then we look at the number 5, and there's only 1. So my LCD is going to equal 2 to the 4th, which is 16, by the way. So 16 times 15. 30. 5 and 8. Put a 0. 1 times 6 is that. 1 times 1 is that. So my LCD here is 240. Oh, I'm lying to you because I forgot about the X's. I've completely forgot about the X's. Now, let's go back and let's look at the X's. In the first denominator, you see 1. In the second denominator, you see 3. Step 2 says it's the product of unique factors where the greatest number of times it appears in any one factor. So you got x to the first and x to the third. So this is going to have to be x to the 3. And that's going to be your LCD. Does that make sense, everybody? Yes or no? How are we looking? How are we looking? All right, now, I'm going to be honest with you. Finding the LCD for numbers, personally, I think is more difficult than finding the LCD for a rational expression. Okay? Rational expression LCDs are very simple. You're just going to multiply the unique factors. You may have to factor something. You may not. Let's look at a simple example. Same directions. Find the LCD for 7x over x plus 2 and 5x squared over x minus 2. Step 1, you're going to completely factor each denominator, just like in the step above. So I look at my first denominator. It's x plus 2. It's already factored. The second denominator, x minus 2. That's already factored. Step 2, we know our LCD is going to equal the product of unique factors. So my first factor is x plus 2. My second factor is x minus 2. And it's the product of unique factors raised to a power that is equal to, oh my God, even the wording is crazy. I forget it already. Each raised to a power equal to the greatest number of times that factor appears in any one factorization. You only have one of them for the x plus 2. And the x minus 2, you only have one. There's your LCD. See what I mean? It's much easier. It's much easier than the number thing. Okay? Are there any questions? All right, let's get a little bit more difficult now. So we're going to find the LCD for 6m to the second over 3m plus 15 and 2 over m plus 5, or quantity m plus 5 to the second. All right, so here we go. We'll do this together. Step 1, you got to factor the denominators. So the 3m plus 15, I can factor a 3 out. So that's going to give me 3 times the quantity. Oops, sorry. 3 times the quantity of m plus 5. Now the second denominator. M plus 5 to the second. It's already factored. It's just m plus 5 to the second. Remember, m plus 5 to the second means m plus 5 times m plus 5. Okay? Now, step 2. The LCD is going to equal the product of unique factors. Let me show you all the unique factors. Actually, there you go. I wanted to do them in separate colors. So my unique factors are a 3 and the m plus 5. And the reason why I did m plus 5 in green is because they're the same in both denominators, the m plus 5. The question becomes, how many 3s and how many m plus 5s? So the number 3, I only see one of them. So it's 3 to the first. The m plus 5, you were looking for the number that is repeated the most in any factorizations. In the first factorization, it's only raised to the first power. But in the second, it's raised to the second. So your LCD is 3 times the quantity of m plus 5 to the second power. Does that make sense, everyone? Are we all on the same page so far? All right. One more example for today. That's it. Find the LCD for t minus 10 over t squared minus t minus 6 and t plus 5 over t squared plus 3t plus 2. All right, process doesn't change. Step 1, let's factor. T squared minus t minus 6 factors down into t minus 3 and t plus 2. For the second denominator, that will factor down into t plus 1 and t plus 2. Step 2. We're going to multiply. The LCD is going to equal the product of unique factors. Okay? So, you got a t minus 3, a t plus 2, and a t plus 1. Now, I need to find the exponents for this. So if I look at both factorizations from above, the t minus 3 only appears once. So 1t minus 3. The t plus 1 also only appears once. The t plus 2 appears once in both of them. But it only appears once. That's the maximum number per factorization that I see. So I'm done. That's going to be my LCD. Does that make sense, everyone? All right. So I'm going to call it a day.